Yeah, that's what I'm thinking. Alrighty, guys, welcome back to Calc 1 Honors. Last time we finished up with a promise of a certain special limit coming back. We are not quite ready to approach the problem where that limit shows up. Remind you what that was. And I think we're getting quite close to looking at derivatives. So let me take a quick look at your syllabus here. We'll do this together and kind of let you know where we're going in the next few days. Hope everybody had a safe, happy, long weekend. Here we are. So we finished talking about limits at infinity, which means we're ready to start talking about rates of change and derivatives, which is kind of the first big piece of this class. This class is kind of primarily focused on differentiation and applications of the derivative. And at the end of the class, we'll be looking at the introduction of this concept of an integral or antiderivative. But now that we have finished 2.6, we've gone through all of the sort of preliminary limit rules and theorems that you need in order to actually start cooking up some derivatives. So today I'm going to introduce the concept of a derivative, and we will do some calculations. I'm going to remind you some things from pre-calculus, and then we'll look at our first few derivatives. This means that we are getting close to the next student teaching. Of course, I do need everybody to send me their honors projects ideas. I think I have an email or two that I haven't gotten to yet that talked about these, but there's a few folks that haven't sent me those. So if you haven't, please do go ahead and do that. The next student teaching assignment is Radha and Natasha, who are doing 3.1, which is on the power rule and derivatives of exponential functions. And then that'll be shortly followed by Nikita's lecture on 3.2, which are the product and quotient rules. We are very close to those guys. So those will be showing up next week. Probably next Monday, we'll do 3.1. So I need the three of you, Radha and Natasha and Nikita, to all meet with me sometime this week and go over at least the basics of how you intend on doing the student teaching stuff. Because again, next week we will be digging into that. We did lose a day this week, right? So normally we'd have 3 days to meet instead of having the Monday this week. We had the holiday. So we might not be ready for 3.1 until next Wednesday, but next Wednesday at the latest, right? A week from today. So if you guys could please make a point of coming by office hours, share with me how you intend to do the lecture. You're going to do it live, you're going to pre-record videos, you're doing a slideshow, and then run through the basics with me, the theorems you intend to cover, the explanations you intend to give, the examples you intend to do, at the very least. Okay, I appreciate that, William. Yeah, I haven't, like I said, I do know I have a few emails in there regarding the stuff that I haven't gotten to yet, so I'll take a look and reply to that later today. All right. So let's do the thing. This is MAC2311 section OH1, which is a Calc 1 honors class. Today is the 8th of September, 2021. And on this day, we're going to talk about rates of change. And we're going to introduce the derivative, which is a big deal. A big deal. Calculus is basically comprised of two main operations: differentiation and integration. Differentiation is, the process of finding the derivative of a function, and integration is something else. We'll talk about that later. Let's do it. I'm going to present this from a kind of intuitive standpoint first. Okay, this is kind of convenient because I've been using an analogy with my pre-calculus students to sort of help them understand rates of change. Pretend like the graph here, what should I call this? How about just f of t, and I'm going to use my independent variable here as t, because it's going to stand for time in hours. And f of t, this is going to stand for distance in miles. And I'm going to chop my horizontal axis up. Let's call this 2 units here. Okay. So here's what I'd like you to imagine. I'd like you to imagine that this function, the function graphed above, outputs the distance I am from home t hours after leaving on a drive. All right, so I'm going to, at time t equals 0, I'm going to get in my car and pull out of the driveway. And then I'm going on a trip. Maybe I'm just going to drive straight north. Pretend there's a road out here that just goes straight north. I'm going to pull out of my driveway and just get on that road and go. I'll mark this axis 1, 2, 3, 4, 5, 6, 7. So I'm driving for 7 hours. And let me chop up the vertical space here. We'll say each one of these is like 20 miles. Let's say 50 miles, 60 miles, 100 miles. Why not? Somewhere. So if you wanted to interpret what's going on here, right? I'm getting in the car at time t equals 0. I'm driving north. The y values along this graph are the distance I am from home, and the t values, or the inputs along this graph, are the time since I left. So for example, 2 hours after I left, I am 100 miles from home. 3 hours after I left, I am 300 miles from home, and so on, right? Maybe 350. If you want to know on average how fast I was going over that first 2 hours, so let's just review. My average velocity, or velocity is like speed, but with a direction. My average velocity over the first 2 hours is f of 2 minus f of 0 over 2 minus 0, right? You take the distance covered and divide by the time. So f of 2 is 100. F of 0 is 0. And 2 minus 0 is 2. So this is 50. And the units would be the units of the top divided by the units of the bottom. So that's 50 miles per hour. In other words, over the first 2 hours of this trip, my average speed, if you want to call it that, instead of velocity, is 50 miles an hour. That does not mean I was going 50 miles an hour that whole time. That average velocity, you remember from your pre-calculus classes, I hope, is the slope of this little secant line, right? If I want to know my speed or velocity at any one particular moment, so let me put this in here. This is the slope of the secant line, the dashed line that I've drawn in there. If I want to know my speedometer reading, my actual speed, my actual velocity, like what the speedometer in the car says, first, if I want to talk about my actual velocity at a particular moment, you need to specify a particular t value, a particular time. So let's say at t equals 2, this would be, this is a little harder to calculate. But I can tell you geometrically what it would be. It would be the slope of this purple line here. Which is called a tangent line. So the dotted blue line, the thing we call a secant line, hopefully you remember from a previous class, gives you an average velocity. If you want my actual or instantaneous velocity, the speed I'm going at that moment, the thing that you'd see on your car when when you look at your car and you see it's got a little, it's got a gauge there that tells you how fast you're going, called the speedometer. That number would be the slope of this purple line. Why is it hard to calculate the slope of the purple line? Well, there's no run, right? If I'm trying to find a slope, usually it's a rise over a run, like it was here for this blue line. That was not hard. I take this rise, which was 100, over this run, which was 2, and I get 50. Okay, great. For the purple line, I really only have one point on here. I don't have like a second point that I know a priori to be on that line. I'm not forming that purple line by thinking about 2 points on the original graph. What I'm really trying to do is to find the slope of the curve at that point. But you know that curves don't have slopes. Their slope is always changing. That's what makes them curves rather than straight lines. So how do you do that? There's more than one correct answer, but the answer that Isaac Newton and Gottfried Leibniz discovered contemporaneously in the 16th century was to say, find a formula for this blue line independent of the numbers like 1 and 0 and 2, just in terms of say a and a plus h. And then, and this is the big idea, use a limit to drag this to drag this point over on top of that point. So you slowly move this point over here. And as you move this point and this point closer and closer together, the blue dotted line becomes the purple line. So let me say in words here, to find the slope of the tangent line, which is the purple, use a limit to move the 2 points for the secant line closer and closer together. All right, so that's the idea. My actual velocity at any moment in time can be thought of as the slope of the tangent line to this graph, this position graph. And the way you're going to calculate the slope of those tangent lines, the way you're going to find the slope of the purple line above, is to use a limit to take a secant line and slowly bring the 2 points together. I think I have a Desmos graph to illustrate this for you. I'm pretty sure I have one baked in here. So let me sign into Desmos and see what I got. Let's jump over here. Thought I had one saved. Yeah, that's it. Yeah, victory. Okay. Those are two curves. Slope of the tangent. Thought I had another one. So partial sums and total entitled. And let's back in the front. Also questions from students? No, okay. So it looks like I do not have the picture of the secant line becoming a tangent line, but I can show you here what tangent lines look like. All right. So what we're going to try to do is, given any function like the red function here, we're going to try to, if you tell me a particular x value or particular input like 4, we're going to try to find the slope of the purple line. And the purple line is the closest thing to telling you the slope of the curve, if such a thing could exist. It tells you at that point, kind of how quickly the red curve is changing. So for example, over here, when x is equal to -2, this red curve is clearly decreasing. And for every kind of step we take over, we're going down a certain amount. Now, the amount you go down for every step over changes from point to point. But at that point, the closest thing we can say is that right here, we're decreasing at a certain rate, at a certain speed, about 4 units per step. So in other words, the tangent line gives you the instantaneous rate of change. That's the actual velocity. All right. And this is kind of the important connection between rates of change, average rates of change, and this new object we're going to play with called the derivative. Okay. So let me show you what it looks like to drag the 2 points from the secant line to a single point. So average rate of change to instantaneous rate of change. Average rate of change, these are secant lines. And the instantaneous rate of change, these are slopes of tangent lines. And it's that slope of the tangent line that we're so very interested in, because that's going to tell me my velocity at a given moment. It's going to tell me in any sort of application problem the exact rate of change. It's also the thing that's called the derivative. I'm going to draw a picture that should be somewhat familiar to you, the secant line picture. But this time, call this right here A. And the point on the graph right here is A, comma, f of A. So the graph, I'm sorry, the graph is of the function of X. If I let H be a small positive number, maybe something like this, then A plus H would be just to the right over here. So this point is A plus H, comma, f of A plus H. Then I can draw the secant line. To these points. Connecting these 2 points. There's that secant line. What I want is the tangent line to F at this point right here. I'll try to sketch him in. He should look something like this. So kind of intuitively, you can think of the tangent line as like if you had a little guy skiing along this hill, right? You know, like snow skis skiing along the hill. The tangent line is parallel to the guy's skis. So as he comes over the top of the hill, his skis are perfectly level. As he's rising up here, his skis are pointing up. As he's going down here, his skis will be pointing down. Right at this moment, just a little bit past the top of the hill, his skis are starting to point down again. You can think of that tangent line as being like the skis. Question is, how do I go from the secant to the tangent? How do I get the slope of the purple line? I don't care about anything but the slope. The slope of the secant line is the rise over the run. That's the y value here minus the y value here. Divided by the x value here minus the x value here, which is A plus H minus A. So this is something you've probably seen before. This is called the difference quotient for the function f. And then the big idea is this. You hold this point here. He doesn't move. But we slowly bring this point over. And the way you do that is by bringing this x value over. And the way you do that is by sending h to 0. So if you send h to 0, then a plus h goes over to a. And as that happens, this point is slowly walking along the graph up to meeting this point. And when they do actually meet, instead of having a secant line with 2 points, you'll have the purple tangent line that just kisses the graph at that 1 point in that perfect slope. Which means the slope of the tangent slope of the tangent line, I should say. That is the limit as h goes to 0 of this line. F of A plus h. That's f of A. And this is the thing we call the derivative. This thing is, by definition, f prime of A. So here's the notation we use, or at least the notation I'll be using at the start is this prime notation. This little apostrophe mark here is read as the word prime. And it is, by definition, the limit as h goes to 0 of f of a plus h minus f of a divided by h. This is a nice, handsome, important rule or definition. So something we definitely want to save. In other words, the derivative of a function at a is the slope of the tangent line at a. So here, this kind of generic looking function at a, I don't know what the slope of this line is, but I know it's negative. It doesn't look like it's too big. You can start to make conjectures just based on the geometry. On the other hand, if you have an algebra formula for the function f, then you can compute this limit, and that will give you the derivative or the slope of the tangent line. So kind of one other thing to make sure you remember. Just putting these two things together, this is the slope of the tangent line to f at x equals a. Probably also worth kind of boxing that. So you remember that these things are intimately connected to each other. All right. One of the sort of classic examples here is a falling object. It said that Newton was inspired, his discovery of calculus was inspired by watching an apple fall from a tree. It's not really known whether that's true. I don't think Newton would tell us if it wasn't, because the story is so famous, even if you were alive. But let's start with an example like that. So what I'd like to do is find the speed of an object that's falling as a function of how long it has been falling. And in order to get started with that, we need to know a little bit of physics. So here we go. All right, so for example, actually, let's start with something a little bit simpler. Before we look at the physics example, let's just find the equation of the tangent line to the function f of x equals x squared at x equals 2. So let's start simple. Let's just see if we can find the equation of the tangent, and then we'll look at an application problem. You know what x squared looks like. So here's 1, here's 2, here's the point on the graph. I want to find the equation of this purple line. We know the y value on the graph there. This is 2, 4. So along the graph of x squared. And recall that to find the equation of any line, We need first the slope, and slope I'll call M. And second, we need a point on the line. You don't need the y-intercept. That's the thing I'm trying to make clear here. To find the equation of a line, you don't have to just jump to y equals mx plus b, and sometimes you can't. What you do need is the slope of the line and then any point on the line. So that point on the line, I'm going to call that x1 comma y1. And then the equation of this line is y minus y1 equals m times x minus x1. This is sometimes called the point slope formula. All right, and it's definitely something you need to remember because we're going to use this every time we try to find a tangent line. And we'll be finding lots and lots of tangent lines. I promise you there will be a problem on the first exam that just says find the equation of the tangent line to this function at this point. So again, to find the equation of any line, you need the slope of the line and a point on the line. That's it. Now we know the slope of this purple line is going to come from the derivative. So we're going to have to calculate the derivative to this function at x equals 2. A point on the line. Can anybody tell me a point that is for sure on the purple line? Who can help me out?
2, 4.
Yeah, the point of tangency, right? Just like a secant line, you know, there's 2 points on that secant line. They're the 2 points where you touch the graph. There's 1 point on the tangent line that you can always be sure of, and that's the point of tangency, the point where the tangent line touches the graph. So for the point, you're pretty much always going to use the point of tangency. Which here is 2, 4. And if you look back on that Desmos graph, you can see a little bit what I'm talking about. So the point where the line is tangent, that's always a point that's actually on the tangent line. It's also a point that's on the curve. And since you generally know what the curve is, you just don't know what the tangent line is, you can come up with your point pretty easily. So kind of here's a picture, right? And this point, the point of tangency, which in this case is 6, 4, is shared. It's on the purple, it's also on the red. So for us, that point is 2, 4. The slope is the fun part. The slope here is f primed of 2. I don't know what that is yet. But I know that it should be the limit as h goes to 0, f of 2 plus h minus f of 2 all over h, right? I'm just taking that definition of the derivative, the definition of f prime of a, and I'm plugging in 2 for a. Take a second, make sure you see where all the pieces are. This is precisely the reason why you saw so many things like this in your pre-calculus class. Certainly, I hope you saw many things like this in your pre-calculus class called difference quotients, right? Because the derivative is a limit of a difference quotient. From here, there's nothing to it but to do it. We've got to plug in, calculate that limit. Quick comment, I guess, f of 2 plus h, there's never anything you can do to like split this up. It's not f of 2 plus h or anything like that. I should make that note. This is an honors class. I don't think you guys would do this, but All right, that sort of shit never good, does not work. The only thing that does work is using the definition of the function. F of anything is that thing squared. So f of 2 plus h has to be 2 plus h all squared. And f of 2 has to be 2 squared. All of this is over h. Everybody with me? Okay. Now, if I want to evaluate a limit like this, I can't just substitute directly, right? First thing that comes to mind usually is, oh, just direct substitution. This is a rational function. The top's a polynomial of h, the bottom's a polynomial on h. Maybe I can just plug in. But if you try that, the bottom is 0. The top is also 0, but the bottom is 0. 0 over 0 is an indeterminate form. We get into trouble there.
I'm so sorry, you were cutting out. I'm a little bit confused why they're squared now.
Well, this is f of 2 plus h. So what is f? What is the function f? It's the squaring function, right? F
Okay.
x is x squared. F of my dog would be my dog squared. F of k would be k squared. And f of 2 plus h is 2 plus h squared.
Okay, thank you.
Here, just plugging in, yeah, what the function is. All right. Like I said, you cannot compute this limit using direct substitution, at least not in this form, because the bottom is 0. That's no good. But I can expand out the top. So 2 plus h all squared, that's 4 plus 4h plus h squared. All right, we FOIL it out. 2 times 2 plus 2 times h is 4h plus h squared. And then you've got minus 2 squared, that's minus 4. And that's all over h still. Now, of course, the 4s are going to eat each other up. There you go. And then what's left has a common factor of h that we can bring out and cancel with the denominator. So I've got 4h plus h squared all over h, which is the limit as h goes to 0 of h times 4 plus h all over h. And now these go. Left just the limit, h goes to 0 of 4 plus h, which is 4 plus 0, which is 4. So we just calculated our first derivative. We just found that the function f of x equals x squared has derivative, which when evaluated at 2 is equal to 4. In other words, if f of x is x squared, then f primed of 2 is 4, which means the slope of that tangent line up there is 4. So now we've got our point, we've got our slope. I just have to use my point slope form. So I'll take all this over here. So finally, the tangent line must be, I'm just using my point slope equation here, my point slope form of the line. Y minus y1, which is 4, equals the slope, which is 4 times x minus x1, which is 2. And you could leave it like this. This is fine. Or if you really want to put it into the slope-intercept form, this is 4x minus 8, minus 8, plus 4 is minus 4. So you could write this as y equals 4x minus 4 if you want. Either one's fine though. I honestly prefer the first one. But that's it. That is our first ever derivative and tangent line calculation. Take a second, see if you have anything you'd like to ask. Okay. All right, so this purple line right here, that tangent line, has slope 4, and if you like, y-intercept -4. Kind of what that tells me is that this function here, if you ask how fast is this function growing when x is equal to 2, I would say it's growing at speed 4, whatever that means. It means that's the instantaneous rate of change for that function. Right at that moment, if this was describing a position of a car, and I would say that that speed right there is this tangent slope for whatever units, miles per hour. All right. Since the natural thing to want to do here is to talk about speeds and velocities, I feel like we need to look at least one problem which does that. So we'll return to our falling object problem. Say at time t equals 0 seconds, I dropped my calculus book into the Grand Canyon. All right, so I've just had it with calculus. I'm not fucking with this stuff anymore. And I say, okay, I'm gonna let it go. Just gonna drop it into the canyon. Canyon's quite deep. It is a fact of physics that the distance the book has fallen after t seconds is, we'll call it f, or fall. F of t equals 16 t squared. This is coming from Newton's law of gravitation. It's actually kind of cyclic logic, but on the surface of the Earth, things fall with a constant acceleration of about 32 feet per second, or 9.8 meters per second squared. And there's a factor of 1/2 that comes in from an integration step, but don't worry about that. This tells you just how far the thing is falling. All right, so if I want to know how far is the book fallen after 1 second, I plug 1 into this. Oh, it's fallen 16 feet. How far is the thing fallen after 2 seconds? You plug t equals 2 in here, and you get 16 times 4, 64 feet. You want to know how far this thing has fallen after 3 seconds? You plug 3 in here, you get 16 times 9, whatever that is. All right, this tells you how far the book has fallen. I want to find the velocity of the book at t equals, say, 2 seconds. And a formula for the velocity at an arbitrary time, say t equals a seconds. Okay. So first, is it clear what we're trying to do and what we have to work with? This function doesn't have any speed information inherent to it. It has distance information, right? It tells you how far the book has fallen. The thing I'm after is the velocity or speed at 2 seconds and in general. So the velocity at t equals 2 seconds is f prime of 2, which by definition is the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Very similar to the calculation we just did. In fact, the only difference is going to be that 16. So let's see what we get here. Then h to 0. F of 2 plus h is 16 times 2 plus h squared. And f of 2 is 16 times 2 squared. And all of that is divided by h. Factor out the 16 and everything becomes the same as it was before. And there's a lesson to be learned there. That's that constant multiples like the 16 times t squared play very nice with respect to the derivative. So I'll bring the 16 out and I just have 2 plus h squared minus 2 squared all over h. I'm bringing the 16 all the way up. I can, in fact, bring the 16 out past the limit. Remember, one of my limit laws is that constant multiples come out. So this is 16 times the limit as h goes to 0 of this stuff, which is 4 plus 4h plus h squared minus 4 h. It's the same limit that we had in the previous one. 4's go, and we have 4h plus h squared over h. So that's 16 times the limit as h goes to 0 of 4 plus h, which is going to be 16 times 4 plus 0, which is 64. Oh, I forgot to mention the units here. The units up there, this is in feet. So this would be feet per second. It's falling at 64 feet per second at that moment. So like if the book had a little speedometer on it that told you how fast the book is going at that moment, at that exact moment, it would read 64. This limit was the same as the one we just did, nothing too exciting. But the second one is going to be more fun. We want a formula for the velocity at t equals a, just some arbitrary number. Paper first, are there any questions on the calculation here? Very good. All right. So what about the velocity at an arbitrary time? This generic time. The velocity at t equals a seconds. Well, this would be f primed of a. Again, by definition, that's the limit as h goes to 0 of f of a plus h minus f of a all over h, which is limit h goes to 0, 16 times a plus h squared minus 16 times a squared. Because what is f of x? What is f of t? It's 16 times 2 squared. So f of a plus h is 16 times that square. F of a is 16 times a square. All of this is still over h. Similar to the other guys, I can factor out the 16. I can bring the 16 all the way out from past the limit. And what's left here is a plus h squared minus a squared r over h. So as you solve these problems, where you're calculating derivatives, speeds, slopes of tangent lines, using the limit definition of the derivative, this thing, start to look for patterns. Try to find some patterns. Hopefully you're seeing some of them now. Like this constant that was a part of this function pops out, and it always pops out. I have here 16 times the limit as h goes to 0 of this piece, which is a squared plus 2ah plus h squared, following it out, minus a squared all over h. And the a squareds eat each other up. So we have 16 lim h to 0, 2ah plus h squared over h. And my goal, remember, is to get rid of this guy down here so I can plug in 0 for h. Can't do that while he's down there. In order to get rid of him, I need to factor in h from the top. Cancel at the bottom. So the top would then be 2a plus h after factoring out that h. Downstairs here, I still have this guy, and now those will cancel. So this is 16 times lim h to 0 of 2a plus h. And just like we did in the other ones, you can now send h to 0. So you got 16 times 2a plus 0, or just 32a. Because we've taken so much space to write this, i.e. f prime of a is 32a. So if you want to know the speed of this book at any time, just plug that in for a. Speed or velocity at t equals 4 seconds or 1.5 seconds. That would be f prime of 1.5. Should be 32 times 1.5. 1.5 is 3 over 2. 32 over 2 is 16. 16 times 3 is so I can't do arithmetic in my head. Yeah, 48. And this would be feet per second. Nobody asked me for the speed at time 1.5 seconds. I'm just using this as an example to show kind of why this is useful. If you calculate this in general, then you can answer any question of this form, right? What is the speed or velocity at this time? Once you have this, you just plug in. We could solve the first part, right? If I wanted to know the speed at time t equals 2, I'd just plug in 2 here. I get 32 times 2 is 64. That's what we found. So by doing this in general, you give yourself a powerful tool, which is this thing. Questions here? All right then. Let me see how we're doing for time. 11:57. We've got a little bit of time left. There's a bunch of fun stuff we can do with derivatives. I don't want to overwhelm you. I do want you to be comfy. So let me just show you one or two little things. Other ways of thinking about the derivatives. Okay, so first, yes, f prime of a is the limit I gave you, but it could also be defined as the limit as x goes to a of f of x minus f of a over x minus a. This is one way to do it. Some people call this the limit definition at a point and call the other one the regular limit definition. It's the same thing. It's just instead of writing a plus h here for x, you write x itself. And then instead of sending h to 0, you send x to a. Another way to think of f prime of a is as the instantaneous rate of change for the function f at x equals a. And then finally, another way of thinking of the tangent line you can kind of think of the tangent line at any point as being the best linear function to approximate f. And this is something that's going to come back. So depending on where you're looking, that's not the tangent line. To f of x at x equals a or b, wherever, is the linear function, the unique straight line that stays closest to the graph of f at x equals a and nearby. Actually, let me rephrase that. Let me just say nearby. Near x equals a or b, whatever you're looking. So what do I mean by that? I mean, if you think about all the lines that pass through this point, the line that kind of stays closest to the black curve on both sides is the tangent line. So if this line right here had any other slope, then it would deviate from the black curve faster than this purple guy does. What that means is that this is the best approximation. If I want to define the y value on the black curve over here, but I couldn't do that for whatever reason, it's hard to calculate, I could find the y value on that tangent line instead. To people who study a certain kind of geometry called differential geometry, this is actually the definition of the derivative that they use. They say the derivative is the unique linear function that minimizes the distance from the original to that linear function on some open interval centered at A. So of all the lines that go through this point, the tangent line is the one that stays closest to the graph of F. And that will be very useful in one of the application sections we're going to look at. All right. In parting, I have a question. Suppose f of x is the sine function. What is f prime of 0? F prime of 1. Sorry, let me not do 1. How about pi? F prime of pi over 2. And f prime of a in general. So this is something I'd like you to think about. To answer any one of these, you would have to set up a difference quotient involving the sine function. And you remember at the end of class last Friday, I mentioned a particular limit that was going to be very important. We will see that limit next time, and I will work it out for you as we cook up the derivative of the sine function. Kind of generally, before we do that, I would like to introduce the concept of studying the derivative as a function in its own right and comparing the graph of f to the graph of f prime. But once we've done that, we will be ready to go ahead and calculate the derivative of sine in general. I would like for you guys, since this is an honors class, to look at the graph of sine and just try to figure out a few of these. So let me actually do some of that with you really quick. Here's the graph of the sine function. Here's 0, here's pi over 2, and here's pi. What do you think the slope of the tangent line to this graph at pi over 2 could be? Yeah, it looks like it should be 0, right? If you again kind of think of the skis moving along the graph here, the skis would be pointing straight horizontally. Over here, at x equals 0, what do we think the slope of the tangent line might be there? Yeah, this kind of looks like it would have slope 1. In fact, if you kind of just look at this little part of the sine function right in here, it looks a lot like the line y equals x, which has slope 1. And then over here, pi, what do we think the slope of the tangent line might be? Yeah, good, -1, very good. Okay, so here's some points. We said 0 at x equals 0, the tangent line has slope 1. So I'm going to plot the point 0, 1. We said at x equals pi over 2, the slope of the tangent line should be about 0. And at x equals pi, the slope of the tangent line should be about -1. Let me make all of these blue. And I'll add in a couple more for you out here. At 3 pi over 2, that slope looks like it should be 0 again. I'm just graphing these as though they're their own thing. And then let's do this one over here at like -pi over 2. The slope of the tangent there should be 0 as well, right? So -pi over 2, 0. Let's graph that. Okay. What do these blue points kind of start to look like?
Cosine.
Yeah.
I have a question about the sine one.
Yes.
How is there a tangent line at 0? Doesn't a tangent line just touch one point of the graph?
Not necessarily. Not necessarily. So tangent lines can overlap completely with your graph. It's not the defining characteristic that the tangent line only touches at one point. It's the tangent line matches the slope and must touch at that one point. Now, it is true that the tangent line to the red curve is y equals x. And if you look very closely, you'll see that the green and red actually do only touch at that one point. They're very, very close to each other nearby, but the only place they actually touch is right there at the origin. So I understand what you're saying. I think it kind of looks like maybe the tangent line would sit on top of the red graph exactly. That's okay. If that were to happen, that would be okay. That wouldn't violate any definitions. It might feel a little strange, but even though it very much looks like that, it's not actually happening here. But if it did happen, that would be okay. There are functions where that does happen. For example, if I look at y equals 2x, the tangent line anywhere would have slope 2. So the tangent line to a linear function, right, no matter where I do the calculation here, the tangent line is going to be the same line. This guy is his own tangent line, which is kind of silly. So that sort of thing is allowed. It's not necessary that the graph only touch the tangent line at one point. But this is neat. So by thinking about tangents, just a few of them.
Okay, and it's like in this situation, like it crossed the line, that's completely fine too.
Yep. Yeah, there's no kind of geometry rule about how the tangent line can interact with the original function beyond saying it goes through the point of tangency and has the slope that best matches the original function's slope there.
Okay, thank you.
Yeah, of course, of course. All right, so we've resolved these guys, right? F prime of 0, we're pretty confident is 1. F prime of pi, we're pretty confident is -1. F prime of pi over 2, pretty confident is 0. But you should actually do the calculations to verify. And then F prime of A, so we're starting to think that this guy is maybe 1. This guy is maybe -1. And this guy is maybe 0, we should check. And then this guy, we're starting to think is maybe cosine of A. And next time I'll prove that to you, but it's going to require some work with trig identities and limits. So I do not want to rush it. All right, that's where I'm going to leave it for today. Next time, we're going to talk about the derivative as a function, studying that kind of in its own right. And then we'll calculate a few very important derivatives, including the derivative of sine. Then next week, let's see. So next week, we'll be moving on to the basic differentiation rules and some other trig derivatives. So like secant, tangent, all that other good stuff. The way we're going to get these is by using things like product and quotient rules on the stuff that I'll pick up for you tomorrow, Friday. That means that 3.1, we're going to be ready for that on Monday, I think. So we should plan, that was Radha and Nikita? What do we have? 3.1. Yeah, Radha and Natasha. You guys should plan to do your student teaching next Monday, which means we need to talk between now and Friday. We need to meet in an office hour. If you can come by today's office hour, that would be nice, although I know you probably haven't had time to prepare anything yet. So please, let's say plan to come by Friday's office hour, both of you, so we can talk a little bit about how you're going to run your lecture, what you're going to cover, all that good stuff. And then who's my other person who's going to be going next week? Product and quotient rules, that's Nikita. Okay, Nikita, if you could also just reach out to me and let me know when between now and next Monday you could meet to kind of begin outlining your lecture and discussing how the student teaching will go, okay? Yep, 1 to 2 p.m. today. That's the office hours, 1 to 2 p.m. You can email it to me. Yeah, email or Canvas message will be fine. All right, is there anything else you guys would like to ask before we wrap things up for the day? Alrighty then, I'm going to go ahead and end the meeting here. I hope you guys have a lovely rest of your day. There is more homework coming out. Take a look on WebAssign, and I will see you on Friday.
Thank you.
Of course.